In this segment, we're looking at some of the alternative methods for multiplying, particularly multiplying in this segment. We'll do division in a separate segment. So we know when we were doing these alternative algorithms with addition and subtraction, we had certain goals for our algorithms. And one of those goals was to help students develop conceptual understanding. So we want our methods to be efficient, right? We don't want to make it extra cumbersome for kids if we don't need to, but we want to help promote conceptual understanding as opposed to just getting answers right, which is procedural fluency. All right, so conceptual understanding means you know the reasons and the whys behind what you're doing. So with the partial products method, I did this verbally on March 13th during class where I talked about some of the pros and cons when we were rushing through everything. But this had been on my plan to make a nice table like this. So remember the day I was asking you to multiply in S20, right? And so we were doing problems like this, right? And I said, how many of you would, if you were sent home with a worksheet of these, and I know you were very relieved when you weren't, if you were sent home with a worksheet of these, how many of you would use the partial products method? And a lot of you said yes, right? That you would prefer to do it in this method. And you have to remember that for you, this is the new method. You already know the steps of the traditional method. So imagine not only having to learn the process of multiplying and be uncertain of your number facts, but also have to learn the steps of the traditional algorithm. That would be much more difficult. So this is something that's easier for students. And again, we've talked about this a lot. Anytime you can separate the requirements where you can do all your multiplying first, oops, didn't mean to cross that out, where you do all your multiplication first and then you do addition last. It is much easier for kids to focus on one activity at a time. Certainly this promotes an understanding of base 10 because we're not just saying 2 times 3, right? This isn't 2 times 3. It is 20 times 30, right? So it's helping students understand base 10 and place value. I like that it eliminates the need for a placeholder because no one understands why we have a placeholder, right? And then the other thing about this is it works so well to model here's a model with base 10 blocks. We were drawing these out on the base 10 graph paper. If you don't have base 10 graph paper, you can just draw it out like this, right? So here's your 36 this way, here's your 24 this way. All right, and we can multiply this times this and see those rectangles that represent each of our partial products. So lots of benefits, right? This is a great use here of multiple representations. All right, so that's a word you want to keep in mind when you write your EdTPA someday. But as is true with all of our alternative algorithms, there's always some cons, all right? And so what we do is we look for a balance of, do the pros outweigh the cons, do the cons outweigh the pros? So certainly partial products method would be horrible in a problem like this. You would actually have 9 partial products. We're not really asking kids to do this by hand anymore. When I was a student in the 80s, we did stuff like that by hand. Not so much anymore. And then the other disadvantage, my daughter learned partial products. And at first I thought it was fantastic until she got to decimals. And my daughter was doing multiplication by decimals and she would correctly move the decimal point like she was supposed to, but then she'd say 20 times 40. And no, this isn't 20 times 40 now. This is 2 times 4/10. So all of a sudden the benefits that had happened over here where it was recognizing, oh wait, I mean to go up here, recognizing the value of each number, suddenly she was continuing to use this process, and yet as she was multiplying these, she wasn't correctly understanding the value of each number. So as soon as my daughter got to decimals, suddenly I was not nearly as sold on this being a fantastic way to do things. But I think this would be a great starting point. At this point, there was, and again, I've said this many times throughout your teaching career, different methods and different programs are going to phase in, they're going to phase out. You're going to have to try to bend with a lot of different ideas that come in and out. So for a while there, these alternative methods were very popular. At this point, Common Core favors that you begin teaching with methods such as partial products to help students develop conceptual understanding. But the Common Core right now says that the expectation is that students will eventually move on to the traditional algorithm. But I do think this would be a good starting point from which then you would go on to a traditional algorithm so that by the time students got to decimals, they would be multiplying in the traditional way. So another alternative method that I really wish they had had in the 80s, because the longer the multiplication problem, the more I like the lattice method. All right, so the way the lattice method works is you set up, so for 23 times 35, 23 over here, 35 over here, and then the most time-consuming aspect of the lattice method is drawing the boxes. All right, and then I extended, normally we don't have these lines coming off. I extended those lines though. But notice how we're getting these numbers. 3 times 3 is 9, 3 times 5 is 15, 2 times 3. One mistake I see students making is putting the 6 up here when they shouldn't. 2 times 5 is 10. So if you look at when I multiplied this out by partial products, the reason this works, because down at the bottom, why does this method work? I ask this on every single test every year. If students don't answer it properly on the first time around, I ask it again on the final. So what I want you to notice is that each of these diagonals represents a place value. This is the ones place, this is the tens, the hundreds, and I don't have any thousands here, but this would be the thousands place. All right, and compare the numbers in here with the numbers up here, right? 5 is the only number in my ones place. 9 and 1 are in my tens place. 6 and 1 are in my hundreds place. What that means then, so there's two things you have to do to get full credit on a test. You have to label your diagram like this, right? Don't just say, a lot of people say each diagonal is a place value. Show me, all right? I want to see the picture. Then the other thing that you have to tell me, because what's happening here is that when you put a number into the top half of the box, this number is carried to the next place value. All right, so try this over here. I'm going to pause for a minute and you carry out this one. So like I said, the longer the problem, the better I like lattice, and I really wish they had introduced me to lattice back in the 80s, right? Because this is what we were doing in the 80s in math class. So you do have to carry sometimes. Like I get a 10 on this diagonal, so I'd carry the 1 like up here. Carry a 1. So if we were in class, I'd be asking you who likes this. And I bet a fair number of you would raise your hands. I think it's a cool way to do it. But again, if I were asking you, why did this just work? All right, why did this work? It's because here's my 1s, right? These are my 10s, 100s, thousands, 10,000s, and then finally 100,000s, right? So my final answer here is 113,505. So next on the list here is Egyptian doubling. Okay, and before we get to that though, I want to talk a little bit more about the hidden distributive property, because the Egyptian doubling method is another illustration of how the distributive property hides in our problem. So remember doing this mentally, right? If I did this mentally, I would say, okay, that's just 300, but then I would have to subtract, right? Because I do 3 times 100, that's 300, then subtract what I added in that was extra, that shouldn't be there. So let's pause for a minute and you show me how this illustrates the distributive property if I do this mentally. So as I've said before, if you want to be good at math, you've got to be good at replacing things with their equal. 97 is equal to 100 minus 3. Right? Then when I multiply 3 through, because what I should have done up here with the 300 is then I would have added in an extra 3 9 times, right? So I would have done 300 minus 9, which is 292. Okay, but I can see that here by distributing 300 minus 9. So let me draw an equal sign up here because you would go from this step to this step, finally to the answer. Okay, so anyway, Egyptian doubling method. This is not a method you would ever, I would never suggest teaching this in elementary, although it does have a takeaway that you would use to help your elementary students with multiplication. There is one practical takeaway to this. So anyway, the way that the Egyptian doubling method works is when you're computing a product, you can either pick the 35 or the 28. It doesn't matter. So I showed it both ways. All right. And then you, whatever number you pick, you make 2 columns, right, where I have a 35 and a 1. And then I just double both columns. Okay. So double, 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 double. All right. You can see that I've done that as I move down. And then I keep on, since this is 35 times 28, I stop as soon as I get bigger than 28. And then what I do is I look at the numbers over on the right-hand side and I say, well, how do I make 28 out of this? And so let's see, if I did this, that would be 20 and that would be 8. So these give me 28, which means that if I come over here and I add up these 3 numbers, that gives me the product of 35 times 28. Okay, so I'll let you verify that computationally. Or if I were to come over here, right? So this time I doubled the 28, exact same problem, and I continued to double until I got to a number bigger than 35. Or actually I didn't, but I'm almost to 35. All right, so then I look at this and I say, well, how do I make 35? All right, and to make 35, I would need a 32 and a 2 and a 1, which would mean then if I added up these and this, that would be the correct product. So the reason the distributive property is hidden in here, or the illustration of how this is the distributive property, is what I've really done is I've really replaced 28 with its equal, right? 28 is equal to 4 plus 8 plus 16. Okay. And what I've done when I've doubled, let me use a different color. What I've done is this is really 1 times 35. I'm not showing that, right? But then this is 2 times 35. And this is 4 times 35. Right? And so on and so on and so on. So here's my 4 times 35 when I distribute, my 35 times 8, and my 35 times 16. And so that's how I'm illustrating the distributive property. Now the takeaway that you will actually get from this, that you would actually teach living, breathing students, is that to multiply by 4, you double. All right, so think about it. 7 times 4, or 4 times 7. I'll put it in that order. 4 times 7. Double 7, 14. Double that, 28. Okay, now if you want to multiply by 8, you double. Okay, so 8 times 7. Okay, I could just take my 28 I got when I doubled and doubled, take 28, double it again, 56, right? 8 times 7 is 56. So that's the takeaway you could actually use in a real life classroom. Now, let's practice one more time. Wait a minute, where's my blank document here? Wait a minute, can I move that? Oh, I hope I didn't stop recording. Blank doc, here it is. Add page. So use the Egyptian doubling method right now to multiply, just a little, for a little bit of extra practice. Let's multiply 15 times 31. So again, you can choose to either double the 15 or double the 31. All right, so let's pause for a minute while you try this. So you might have doubled 31 and your work will look differently, and that's totally fine. But in this case, I want you to notice that there's 2 ways I could do this. I could recognize that 31, I need to add all of these, right? So I'd need to add all of this up, right? Or I actually could do this in a different way. I could say, well, 32 minus 1 is equal to 31. I actually could do 480 minus 15. And again, how am I illustrating the distributive property? I'm doing 15 times, so I'm thinking of 31 as 32 minus 1, right? And then I'm distributing to get the 480 and the 15. Or I am thinking of 31 as the sum of, if I were smart, I would use a text box instead here. The sum of 1 plus 2 plus 4 plus 8 plus 16, and then I would be distributing over all of that.